Assalamualaikum warahmatullahi ta'ala wabarakatuh, and hi everyone. My name is Siti Nurshahida Binti Nazli, and I'm going to present my research entitled A Preliminary Study on Fine Particulate Matter and Carbon Monoxide at a Cooking Food Sector. These are the members of my study. Indoor air quality has been one of the most significant environmental problems worldwide due to the impacts towards the building occupants. Despite of this fact, many studies have focuses on outdoor pollutants trends, while lack of information are found on indoor trends. Studies on indoor air quality has been carried out extensively at homes, schools, hospitals, commercial buildings, and office buildings. Yet, none was found in small and medium food sectors, whereby this industry is known to support the economy of Malaysia. A study by McCann et al. Has supported that exposure to pollutants from cooking appliances causes health risks, and study is needed so that intervention can further be identified and implemented, especially at workplace where cooking is conducted extensively daily. Cooking has been identified to cause significant impacts on the quality of the indoor air. Among the more common pollutants indoors include fine particles in PM2.5 and carbon monoxide. Among indoor air pollutants, PM2.5 is at greater concern as they can travel to the lower respiratory tract. It is also identified that carbon monoxide poisoning, even at lower concentration due to cooking appliances, could cause neurological symptoms and increase other health risks, which need further research. Cooking activities also affect the temperature and humidity level at the working environment, where it was found that concentrations of pollutants are even often 2 to 5 times higher in the indoor environment compared to outdoor environment, which expose the occupants to greater effects. Thus, this study aims to investigate the issues of particulate matter in diameter 2.5 and carbon monoxide in a cooking small and medium food sector to fill in the gap of IAQ issues in the occupational setting, especially in the food industries. This study is a case study which is conducted on February 2017 at the food sector, which is expressed as SMEB. This SMEB is a 1,307.4 meter square double-story building which is constructed in 1997 and is located in suburban area about 200 meters from the major traffic. The manufacturing process was located at the first floor, and the product produced by this SME is a coffee powder imported locally and internationally. This SME operated from 8 a.m. until 5 p.m. from Monday to Saturday. There was a total of 60 workers in the SME, and only 16 workers are involved in the manufacturing processes and 7 are involved in cooking. And cooking was conducted 16 times per day. Among the cooking devices used are gas stove, electric stove, and burner. This SME was using diesel in frying activities. It also used G to fry. Electricity was used in the process of coffee roasting, mixing, and grinding. These processes were located at the manufacturing area. Complaints on health problems as well as accidents were identified at this workplace through interview with the manager. In data collection processes, a walk-through inspection was made prior sampling of indoor air parameters. The assessment was adapted from Burroughs 2011 from the book Managing Indoor Air Quality. A walk-through was conducted at the manufacturing areas to identify potential sources of contamination or unusual condition. Through observation, there were various equipments at the study locations that can be a potential source of pollutants besides cooking activities. Table 1 shows the locations of sampling and the equipment and activities observed at the study location, which can be the potential source. The study incorporated measurement on the selected indoor air pollutants based on standard methods and guidelines available. There were 4 sample locations measured at the study location at 4 consecutive days following 8 hours manufacturing processes. Measuring the 8-hour time weighted average are an advantage as it is based on the occupational exposure limits. The type of sampling allows the identifications of the lowest and the highest concentrations of pollutants in the manufacturing areas. Concentration of pollutants near cooking area may be higher than the other locations. However, due to the dispersion ability of pollutants, workers who work at the same breathing zone where pollutants are produced should also be affected even though the concentration might be different. This is according to the Ramachandran 2005. This study therefore measured the concentration of pollutants at several locations in the manufacturing areas to identify these issues. The measurement of the 6 parameters were performed by 2 portable indoor air quality monitors that allows the detection of many variables, which are EVM7 and IQ6110 Grey Wolf. Measurement of IQ parameters were done within sampling area at least 0.5 meter from corners or windows, walls and other vertical spaces, 1 meter away from localized sources and 1 meter above the ground following guideline from the Department of Safety and Health Industry Code of Practice on Indoor Air Quality 2010. All data was compared to the related regulations as shown in Table 2. These standards were set following 8 hours of exposure. Figure 1 shows the trends of PM2.5 at 4 sampling locations at SMEB. From the graph, there were fluctuations of the pollutants during working hours. Greater trends of PM2.5 emissions were observed at location 2, where frying activities were conducted. The concentrations level of PM2.5 had exceeded the standard by ACGIH at 3000 microgram per meter cube, as well as OSHA at 5000 microgram per meter cube at this location. However, at location 1, where frying activities were also conducted, had lower concentration level of PM2.5, which was less than 1000 meter cube per microgram per meter cube. The lowest PM2.5 can be seen at location 3, where roasting of coffee beans was conducted. Grinding process carried out at location 4 also had affected the level of PM2.5 at the manufacturing area. Frying activities at the study locations were using diesel, which could affect the particles level in this area. This is supported by the US Environmental Protection Agency, which stated that PM2.5 is a component of diesel exhaust. PM2.5 is also predominantly generated from activities of combustion, thus affecting the level of such pollutant in the indoor environment. This is through Martins and Carrillo da Graça, 2018. Frying areas recorded high level of particles than other areas due to the higher time of cooking, which was 16 times and was supported by findings by Yamamoto 2014 and Yu et al. 2015. Frying activities at homes emitted about 1.67 to 1366 microgram per meter cube and 0.5 to 50.5 microgram per meter cube of PM2.5. This is from Huboyo. The authors conducted their studies at home from cooking activities, which generated much lower PM2.5 concentration than those emitted in food industries. Particulate matters enter the indoor environment through windows, doors, and cracks, as well as from outdoor sources through improper ventilations. This is according to Santa Maurice 2017. In this study, it was found that these factors play a minor role in the introduction of PM2.5 into the building, especially in cooking and production areas, due to very limited openings available. The reasons are because of regulations do not permit food processing industry to allow openings which could cause infestation of rodents, as well as outdoor air pollutants which could contaminate food in the process. Most of the pollutants were produced from inside the building through cooking processes, and this is also supported by Santa Maurice, which stated that cooking, mainly frying, was one of the main important sources emitted from indoor. Figure 2 shows the trends of carbon monoxide emission at the study location. Cooking areas were found had safe range of carbon monoxide concentration, where both location 1 and 2 had reached less than 3.5 ppm during working hours. CO concentration reached zero level at roasting area after 20-25 hours, where roasting activities stopped. This trend of carbon monoxide at the study locations will not exceed the standard limit except at location 4, where the level of CO fluctuated over the EPA limit of 9 ppm around 10:20 until 12:20. The concentration of carbon monoxide lowered during recess and continued after process started and exceed the EPA standard at 14:20 until 15:30. However, the study managed to investigate the emission of carbon monoxide in the food sector. According to Santa Maurice 2017, carbon monoxide even at low level may cause fatigue to occupants and is produced from combustion process. Workers in food manufacturing industry get exposed consistently within the environment means that they are at greater risk of developing symptoms related to carbon monoxide toxicity. Yamamoto and Yu 2015 that prolonged durations of cooking would produce higher concentrations of carbon monoxide. This is proven at location 3. Whenever roasting activity stopped, the concentration of carbon monoxide was also reduced. As can be seen in the table 3, the average temperature at the sample locations had exceeded the permissible range by the ASHRAE standard, which were more than 26 degrees Celsius. All sample locations had more than 30 degrees Celsius of temperature, which were relatively high. Relative humidity was also found to exceed the range at location 1 with 74%, which exceed the highest range permitted, which is 65%. Other locations had less than 60% of relative humidity. ASHRAE standard had set temperature to be in the range of 60 degrees Celsius to 30 degrees Celsius. ASHRAE 55 to 21 also indicates that an acceptable comfort range of humidity is 30% to 60%. When humidity levels are below 20%, they may cause nose, throat, or eye irritation in some people, while levels above 60% may further accelerate fungal and bacterial growth. According to Yusuf Ahmad and Ismail 2014, the level of particulate matter and carbon monoxide in a building is also affected by temperature and relative humidity. The study by Yusuf may not been measuring the indoor air quality in food manufacturing company, but it's still very much relevant to by this research, as they involve a food industry and they to measure the IQ using physical and chemical parameters. However, the relevance and similarity stopped there because the observed pollutants in their study were given rise by the pollution from the roads, vehicles, and residents nearby the restaurants instead of being caused by the manufacturing processes inside the premise themselves. Hence, further research is needed to tackle this issue. This study had found that temperature was in a critical alarm which need to be tackled faster. This is because all the sampling sites in the study had shown that the mean range of parameter had mostly exceeded the standard limit. According to the U.S. Environmental Protection Agency, to achieve good IAQ, maintenance of acceptable temperature and relative humidity is very important, besides the distribution of adequate ventilation and control of pollutants. For the conclusion, this study had identified the main issues on high particulate matter PM2.5 concentration from cooking activities at food sector, which reached 10 times higher from the standard of regulations. Temperature levels, which also exceeded the permitted range, are also identified in the study. So this finding demonstrated that the agency of IAQ study in food sectors that conducting cooking activities and further study on the effects towards the workers are also needed. These are the references in the study. That's all. Thank you.